Okay, next we're going to work with derivatives of exponential functions that are involving our Euler's number to the power of x. Again, we know this is a constant value. Technically, it's just a symbol representing a rational number. We talked about in the last one how the derivative of e to the power of x is e to the power of x. And when it's a composite figure, we keep the original and then multiply it by the derivative of our power. So our first example, we want to define what we have here. So again, I'm just going to use a different letter here because I shouldn't have used h of x last time, or f of x. H of x is equal to e to the power of g at x. Therefore, the derivative of h of x would be the original e to the power of g at x multiplied by the derivative of g at x. So let's define what we got. Our exponent here, g at x in this case, is actually equal to x squared minus x. Okay? We know from our rule that we're going to keep the original to start. So our derivative of f at x will be very similar to start. We'll do it in blue. It's going to become e to the power of x squared minus x. Nothing changes there. We're then going to multiply it by the derivative of this function here. So we're going to derive what we've called g at x. G prime x would be equal to 2x minus 1. So we'll be multiplying by 2x minus 1 in this case. Can we factor anything out? No. We can distribute, but there's really no need to. This is a good factored form of it. So this becomes essentially our answer here. Okay? And there are other ways to represent it, but we're not going to distribute it. This is in a pretty good factored form. So our derivative is e to the power of x squared minus x multiplied by 2x minus 1. Our second example gives us something where we'll have to work with a product rule. Okay? So because this is x squared times e at x, according to our product rule, being that if we have h at x is equal to f at x times g at x, therefore the derivative of h at x is f prime x times g at x plus f at x times g prime x. In other words, we find a derivative of the first and keep the original, and then the opposite in the other step. So f at x is equal to, we're going to derive our x squared first. This will be our f at x function. The derivative of this is, anyone know? 2x. Good, so we've derived it. And we keep this the same as it was before. Not times, but plus. Plus the value of, we keep our original, so x squared, multiplied by the derivative of e at x. And what is the derivative of e to the power of x? E to the power of x. So it's now derived. Now we can do some factoring in here. So what we'll do is we happen to have e to the power of x in both. We'll common factor that out. So we have e to the power of x as our common factor on the outside. And we're left with 2x plus x squared. Okay. Essentially, our derivative is this value here. We just did some factoring so we could simplify it. I forgot the what? Sorry? Oh, thank you. You're right. Give me one sec.